So remember in our last lesson, we talked about differentiating the natural log function, and we were given two rules. The first rule stated that the derivative with respect to x of the natural log of absolute x equals 1 over x. Well, if I've taken the derivative of the natural log function to get 1 over x, then it stands to reason that the antiderivative of 1 over x dx would be the natural log of absolute x. And in fact, it not only stands to reason, but it happens to be true. The only difference, of course, remembering that we need plus c. So we have a rule for integrating the natural log function, just as we had a rule for differentiating the log function. Now remember, our second derivative rule or differentiation rule was the derivative of the function natural log of u. I said that badly. Let me say it again. The derivative with respect to x of the natural log of u, where u is a substitution, a u substitution, equals u prime over u. So again, the reasonable person would assume that the antiderivative of u prime over u with respect to x would equal natural log absolute u plus c. So remember, this second case rule applied whenever we did a substitution where we let u equal some function of x. Well, then du equals u prime, which is a function of x, dx. So here, where we're looking at u prime dx, this is actually my du substitution. So another way I could write this initial condition for the antiderivative is the antiderivative of 1 over u du. And that equals the natural log of absolute u plus c. No difference between the outcome, just the expression the input expression or the original condition may be written in one of two different ways. So these are the two rules for integrating the natural log. Just like differentiating, I think we just need to do a bunch of examples. So let's first find the integral of 4 over x dx. Well, the first thing I want to do is apply the constant multiple rule. So this is 4 times the antiderivative 1 over x dx. And we have a rule for that. 1 over x dx is just the natural log of absolute x. So that's 4 times the natural log absolute x plus c. And then we could take it a step farther because we are dealing with natural log or logarithmic rules, and we have a rule that says we can put the monkey back up in the tree. So this would be the natural log of x to the 4th. Now notice I've done this weird thing where I've turned the the absolute value into parentheses. And that's a totally legal thing to do only after I've made the conscious decision that anything to the 4th power is going to be positive, and so I don't need the absolute value symbols to hold this x positive, because whatever the x input is, once I raise it to the 4th power, it's going to become positive. So this would be the natural log of x to the 4th plus c. So now let's do an example that involves type number 2. We want to find the antiderivative of 1 over 3 minus 2x dx. Now in this case, we're not looking at x in the denominator. The first case, all we need is a simple x or a variable in the denominator. But in the second case, we have a function of x in the denominator, so we're going to have to do a substitution. So I'm going to let u equal 3 minus 2x, and du then equals negative 2 dx. So let's step back and look at our substitution. I have a 3 minus 2x that I can trade out for a u. That works out great. But now I need to trade something out for my dx. Well, dx is here. Oh, I see. If I subtract, or excuse me, divide both sides by -2, now I can replace my dx by du over -2. -2 then just becomes a constant multiple that can come out front as a -1/2 times the antiderivative 1 over u, and all I have left, my dx is going to become du over -2. So I have a du here. All right, so now take the antiderivative of this, -1/2 times natural log of u plus c. Actually, natural log of absolute u plus c. Now all I have to do is plug back in for my u value. So -1/2 the natural log of absolute 3 minus 2x plus c. So I know this whole thing seems kind of hand-wavy and too simple to be true, but it is true. That isn't to say that every function involving a rational number with the variable x in the denominator or a function of x in the denominator is going to be so easy. Let's look at a case where it is not. I think this time we'll look at a definite integral. Let's find the definite integral from 0 to 4 of 8x over x squared plus 4 dx. All right, so if we sit back and look at this, it's much more complicated than the ones we've worked on so far. But if I notice that 8 is just a constant multiple that can come out outside, the only thing that's really different is that I have an x. But looking ahead, I think if I do a u substitution in the denominator, I'm still going to have an x in my du. And so I think it's all going to work out fine. Let's just trudge ahead using what we know. I'm going to let u equal the denominator, x squared plus 4, and that means du, the derivative of u, equals 2x dx. And there it is, right there. Well, the 2x we're not really worried about, right? Because the 2x just divides through, contributing to the multiple that I will pull out front. And then x dx is my new substitution. So let's figure this out in color because I think it's helpful at this stage of the game. I'm going to trade x squared plus 4 for u. Okay, my 8's going to come out front, so I'm not worried about 8. And then I'm going to trade x dx, all of x dx, for my du over 2. And the 2 is also going to come out front because it becomes a constant multiple. So if I put that together, I'm going to pull the 8 out. When I'm finished substituting du, well, maybe I'll wait to do that. So I've got a 0 to 4 of, well, the 8's already gone. My x dx becomes du over 2. Du, but 2 is just a constant. And then I'm left with 1 over u. So I was able to rearrange the whole thing, replacing every single thing, following the integration symbol, with something new using the substitution. Now I can apply my substitution rule for integrating log functions, and I'm left with 4, because 8 divided by 2 is 4, from 0 to 4 of, oh, I'm actually integrating now, so I don't need my limits there, 4 times the natural log of absolute u on the interval from 0 to 4, which is the same as 4 times the natural log of absolute x squared plus 4 on the interval from 0 to 4. And I'm just going to keep working across the page. So I have 4 times fundamental theorem of calculus, the natural log of 4 squared, 16, plus 4, 20, plus, I'm sorry, that's not true. Fundamental theorem of calculus says minus the natural log of 0 squared is 0 plus 4. And now I can apply some log properties. This is going to be 4 times the natural log. Subtraction tells me that I want absolute 20 over absolute 4. So that equals 4 times the natural log of absolute 5. Plus c. Oh, we don't need a plus c because it's a definite integral. So I was uber careful taking the absolute value symbol all the way through just to make sure I got someplace that I was careful to make sure I got to the right place. But the truth is, way back here, I could have noticed that whatever x is, when I squared, it's going to be positive, and 4 is always positive. Adding two positives is always going to be positive. So I could actually, early on, have quit writing that. I could have started here and written 4 times the natural log of 20 minus the natural log of 4, which equals 4 times the natural log of 5, and been done with it. I was just being super careful to show that absolute value is something that you have to constantly be thinking about when you're dealing with log functions because of the nature of log functions and the restrictions on the domain. So that's the end of the line with these relatively simple substitutions. It'll take a little while to recognize where to make your u substitutions when you're integrating log functions. But you'll get pretty good at noticing that between the u substitution and whatever du and any constant involved in the integration of your u substitution, if you can either replace every single thing or replace most of it and move the other part out as a constant multiple, then you have the right substitution. You just have to plug it in and work to the end. So it's very pluggy chuggy. But sometimes you have to do some rewriting in order to even apply the rule. So let's look at one of those, or a couple of those, I think. Sometimes you get some big ugly thing like x squared minus 3x plus 2 over x plus 1, and you're asked to integrate that. Now, I realize a problem that looks like this makes us both want to run for the hills, but we can't. But we can use some tools that we have, noticing that the denominator is a degree that is less than or equal to the degree of the numerator, which means that we can do long division on this. Now, I hate to do long division. Your textbook shows you long division. I don't get that because you can very easily do synthetic division on this problem. So let's go ahead and do that. I'm going to say I have a coefficient of 1, -3, and 2. And I want to divide it by the solution, -x. So -1, 1 carries straight down. -1 times 1 is -1. That's a -3. So -3 plus -1 is a -4, times -1 is a +4, leaving 6 as a remainder. So if I rewrite this polynomial, this whole rational number, using the division, the results of my division, I see that I am looking for the integral of, 6 is a remainder, so it's a constant. That still needs to be divided by x plus 1. And so this is 1x minus 4. Well, I don't really need to write 1x. I just put it there because I had a 1. So x minus 4 plus 6 that still needs to be divided by x plus 1. All of this dx. And now it's super easy to work with because I'm just looking for the integral of x dx minus the integral of 4 dx plus the integral of 6 over x plus 1, simple substitution, dx. So the first two, x squared over 2 minus 4x plus, well, we're going to let u equal x plus 1. So du equals dx. And now I can make my substitution. So I'm looking for the integral of 6. Well, that's a constant multiple, so I can pull it out front. 6 times the antiderivative of 1 over u du. So I have x squared over 2 minus 4x plus 6 times the natural log of, what was my u, at x plus 1, absolute value, plus c because it's not a definite integral. All right, and then last example involves having to change a variable. So if we're looking at 2x over x minus 1, and the quantity is squared, dx. So if I do a substitution on this, I'm going to have u equals, clearly, x minus 1 squared. And so du then is 2 times x minus 1 dx. Okay, these don't overlap well enough, do they? I have x minus 1 squared equals u, and then I have 2x dx equals, well, I have a 2, but I don't have an x. I have a dx, but I don't have an x. This is crazy. I have a 2x minus, this gets kind of complicated. So when this happens, you actually have to use a process by which you change the variable. So then, and let me write it again just so that it's not confusing once I get going. X minus 1 quantity squared dx. So before I didn't really want to do a u substitution with just x minus 1 because I would end up with a u squared in the denominator, and I don't know what to do with that. But if I go ahead and do exactly that, substitute u for x minus 1, then du equals dx, and I can say further that x equals u plus 1. Now let's see how that helps us. I'm going to take the antiderivative of, well, I have my u, and it's going to be a u squared, yep. And I have my dx would be dx would be du. And 2 I'm not worried about because it'll come out front. And x I'm worried about, but not too much because look, I now have a way to rewrite x using u. So I can actually take care of everything in this problem by doing this method. So I'm going to pull that 2 out front I talked about, and I'm going to let x be u plus 1 over u squared du. Trade dx for du. Now, at first glance, this doesn't seem easier, but it really kind of is, because if I break the fraction apart, so I have u over u squared, well, that's obviously going to be 1 over u. We know what to do with that. Plus 1 over u squared, all du. And we know what to do with that as well, because that's a u squared, which is easy to integrate because we put it up in the numerator as a u to the minus 2. And I have made a horrible mistake here. What is it? Hang on. Let me get caught up. I need to put the integration symbol and then a bracket. Oh, that's ugly. Let me rewrite it. So 2 times the antiderivative of u over u squared plus 1 over u squared du. But that's 2 times the antiderivative 1 over u du plus u to the minus 2 du. And now I can integrate away. So I have 2. 1 over u is the natural log of u, absolute u, plus u to the minus 2 is u to the minus 1 over minus 1. And so that's just 2 times the natural log. Well, u is x minus 1. And u to the minus 1 over minus 1 just means to take away 1 over x minus 1 plus c. And I could clean it up by distributing the 2 in, but I don't necessarily think that's any neater. So that was a lot of ground to cover. I think it deserves a quick recap. Whenever you're integrating a rational function that contains either a variable or the function of a variable in the denominator, you're going to end up with natural log integrals. You can integrate directly because all you have is a variable in the denominator. Bam, done. You can do a quick u substitution if you have a simple linear function in the denominator. Bam, done. When it starts to get a little bit more complicated, you start having to substitute in the denominator, hoping that you can replace everything in the numerator or move what's in the numerator out in front because it's a constant. If you can find a substitution that gives you all the additional elements left over in the numerator by using a substitution, plug it in, bam, you're done. If you can't, you might be able to divide the numerator by the denominator, which can only happen if the degree of the denominator is the same or less. Use synthetic division or long division, doesn't matter to me. Rewrite the rational number and then break it into parts. Do a simple u substitution, bam, you're done. Or, last but not least, you actually have to use a form of substitution where you use the u substitution, u equals some function of x, to solve for x and plug that function of u back in where you can break it apart and bam, you're done. So even though it was a lot of ground to cover, it's not really as complicated as I'm sure it seemed while I was yammering on and on and on, doing example after example.